Morning, everyone. As I just responded, we'll be using the same notebook I used last time, which was my modified version of the data load. I'll just start sharing right now. Can you folks see my
Yes.
notebook? Okay. So I've already kind of logged in and run cells up to this point. This is just the data loader class, most of the code of which we went through last time and some of which we'll look at in a little bit more detail over the course of the next hour and a half or so. So I'll just run this cell, but where we left off, and I'll try and go start a little bit overlap with where we left off last time. So what the fast AI data loader does, and there's several questions last time as well, is why write a data loader when PyTorch has a data loader itself? And as I mentioned, Jemmy wanted to do a few things, provide new capabilities and a lot of customization ability, which means that we want to be able to customize the functions that essentially customize the callbacks. And there are a variety of callbacks which you have the ability to customize if you use the FastAI data loader. So we'll go into this in a little more detail, but a lot of these, the loop methods, which essentially means that they are no ops right now. So before all iteration, after a single item has been generated, before a batch has been collated, after a batch has been collated, or after all iterations. And then there's a whole bunch of methods which are there within the FastAI data loader, which have functions defined currently, which can also be replaced by your custom functions. So you can see that the FastAI data loader provides you an immense capability to customize at many points when you create items, or before or after you create batches, or before or after you run all the iterations to create batches, and so on and so forth. So one example, and he just now begins to provide examples of how you can customize. And there are two different ways to customize. First, we'll go through one method, kind of understand the various nuances of it, and then kind of also point out a different method of doing the same thing. So here's the example of a data loader, and this is a little more incrementally complex way of replacing the CreateItem function within the FastAI data loader. So what you're essentially doing right now is replacing, if you will, this single line function CreateItem, which actually in the FastAI data loader executes this line of code, but instead you want it to do what's being done here. So one way to do that, and there's a little more of a complex way, we'll see an easier way, and also how the easier way is supported by the FastAI data loader in a little while. But let's say we follow this method, which is more of defining a class, which is a random data loader, inheriting from data loader, that is the FastAI data loader you inherit from, and then you modify CreateItem. So here what CreateItem is you just create a random, or create a random function, and then you return the value R, which is the random value, if the random value returned by the random function is less than 0.95, otherwise you stop. So that's, it'll stop randomly. And what Jeremy is trying to emulate by doing this is a stream of data that is coming at you, for example. So instead of just getting the data from a data set, which is fixed length, you can handle, let's say, network data or things like that. And that's what he's demonstrating by creating this particular create item and this method of just creating data. So if you run that cell, and I'm going to run it. So here you can see that it generated, and he just created a L value, and it stopped after 10 values after generating 10 values, because the 10th value or the 11th value is greater than 0.95 for R. And then you can kind of map length on it. And since you've given it a batch size of 4, each of the batches is of length 4.
Is that because you have drop last equals true? That means that,
yes.
any batch size that has less than 4 will just be dropped?
Yes, that's correct. So if it's the last one would be 2, and that gets kind of dropped. Here, for example, if you have more data loaders, what is happening, he's pointing out, is you have more workers. That means you're going and grabbing, you have the workers grabbing more of the data, and therefore, and again, you're creating a new random data loader, and it's grabbing more of them working in parallel.
But excuse me, when you call this rand_dl function, the returned object is going to have an unspecified number of components. So, it could stop after 2, it could stop after 10. So each batch is going to have a different size.
Each batch won't have a different size. The batch size is always 4. The overall stream that you provide to the number of workers will be different. The input,
that's what I mean. Each batch is going to have, say, a batch of 4 elements. Each element in that batch is going to have a different number of
no,
items
you're
in it.
always, no, the batch size is always 4. That doesn't change.
So, okay, I see. So it's just chunking up that stream into batches of 4. I'm sorry. Yeah,
exactly.
Okay.
Exactly. Yeah, so the batch size is always 4. Okay, so this is just some test he does. I'm going to skip over the different way of defining, well, let's run the cell, but I'll come back to this and explain this, because then we'll pursue a different path of explanation of how this works. But let's go through the next few cells, because then the explanation continues with the same thing. Let's stick with the inheritance and the class way of generating the data loader, if you will. The point that he emphasizes then is you can have 2 different ways of approaching the data set or a data stream like we just saw. One where you specify the batch size, and another where you don't. And if you do not provide the batch size, then the FastAI data loader excuse me, does not batch. And what that means is it takes the entire data set that you provided and acts on that. And that's the case when the batch size is none. And this is the same behavior as the PyTorch data loader as well. So I'm just going to run this next cell, and then we'll get into the explanation of what each of these different so we
okay, before you do that, can I ask a question? So what if the batch size is 4 and the data loader, the rand_dl function only returns 2 elements?
Yeah, and if that's a good question. I think if it only returns 2, it will, and if you said drop last equals, then it probably will return nothing. But if you don't have drop last, it'll probably give you the 2.
Okay, got it.
So if you don't provide BS, and remember that letters is the 26 letters of the alphabet that we've already provided very early on in the notebook. So he just defines the data loaders as letters, and he doesn't provide any batch size. So in this case, there's no batches that are created. So when you listify the data loader, what you get back is the entire set of 26 letters. So that's why he checks that the value of L of DS1 is the same as letters, and the length of DS1 is 26. So when you don't provide batches, then the entire data set is given back as input. by the data loader. Of course, we also saw that the data loader can be shuffled, or you can pass in shuffle equal true. So the letters in that case get shuffled. And I think SQB went over, and we will also look at this test shuffle function, which, unlike the test equal function, checks that this value, the L of data loaders with shuffle equal true, is a shuffled version of the second value letters.
So it's just using set, it's just testing the set, that the set of
yes,
each one is the same?
Exactly. That's what you'll find when we go to test shuffle code, if you do. It's in one of the basic foundational Python, probably the very first notebook.
I think it even checks if it's shuffled. Test doesn't necessarily check if it's shuffled, right? Test will just check for unique subs.
Yeah.
Yes.
But the shuffle part of it actually checks if it's even shuffled. You can give it back in the same order, and there's no difference.
That it is not in sequence, that
right.
It is actually not in sequence.
Right.
Yeah. The important thing he's trying to point out, and what I've commented here next, is remember that there are two values, well, there are multiple values, but two related values you can pass to what we're talking about here. One is shuffle, the other is indexed. So if you say indexed equals false, that means that what you're passing into the data loader is an iterable data set, not an indexable data set. So if you go, what that essentially means is that the data set does not have a get item, because that dunder get item is what allows you in any Python class to index into the class. So you can get, when I say index, what I mean is it will return the value at index I. So you can say, give me the value at index 2, at index 3, and so on. But there are data sets like the data set we just saw, which is, hey, I just want a stream of numbers which will stop when my random value is greater than 0.95. Now, in that case, of course, if you list it, then you'll have an index, or if you create an L, then you will have an index. But if you don't, then you just have a stream number of values where the length of it is not determined. And those are generators or iterators, and it's an iterable data set, not an indexable data set. And if that happens, or you want it to be the case, which can be, for example, for very large data sets or very large set of files, you can pass in indexed equals false and load in the data loader. And what the FastAI data loader does, this is again an enhancement to the PyTorch data loader, because the PyTorch data loader, to my knowledge, doesn't support this, is the FastAI data loader checks whether what is passed in, which is this letters, the data set that is passed into the data loader, whether it has a dunder get item. If it doesn't, it'll treat it as an iterable. And if it treats it as an iterable, then it won't be indexed, and it'll just return whatever the iterator or the generator returns. In this case, since we haven't provided any batch size, it'll be the entire 26 letters of the alphabet. Okay, so this just shows you that you can, you can access very large files that you don't know the size of and so on by providing indexed equals false and using a generator in the place of a data set input to a data loader. And that's an enhancement. That's one of the reasons, for example, a FastAI data loader is enhanced or improved compared to the underlying PyTorch data loader. So he just goes on to test that in that case as well, that the data set that is provided is equal to that of the letters. So the L of DS1 is letters, and then checks the length. Then it runs the same test as for two tensors, 0, 1, 2, and 3, 4, 5. And as we talked about before, when you provide just arrays, in this case, of course, he provides T2 as a L of tensors, so it converts it to tensors, or it keeps the type and provides you the answer. But if you were just to provide it an array input, it will still convert it, like he shows in the next example. Data loader converts the arrays of numbers into tensors. And the final example, he just shows that T3 is of type generator, which is used defined elsewhere. And then also we saw this previously last time, that you can define a function called and pass it into the after iter callback, and all it does is sets the value of the f attribute of T3 to be 1, and it just checks that. He also checks that the type of DS4 is T3. The next example, which we saw in the last lecture, but I'll just go through because of the contrast with respect to the prior cell that we just went through right now, which is to say, this particular cell we just went through did not have any BS or batch size specified with the data loaders. The next example actually goes through and illustrates what happens when we use the same letters data set, but we supply the batch size. So here, of course, I had already explained, and you can go back and look at it, combines the list of O, and therefore it's, each batch is what is O. So you'll have 4, because batch size is 4, you'll get A, B, C, D combined together. And then you provide a space and combine it with the next batch. So you'll see spaces between each of the batches. And then you go through the epochs 2 times. That's why there is the range of 2. So you see that you go from ABCD to X. It stops at X because the last YZ is drop last equals true. So that is dropped because it's not equal to the batch size of 4. And you go through 2 epochs. And that's what he checks by that test. He's checking that when you run 2 epochs of the data loader, DS1, what you get as output, because batch size is 4 and drop last is true, and you get the whole letters except for the last 2 characters, and go through it twice. And then when you don't drop the last equals true, that is the default drop last is false, then you get the YZ in that case as well. Now, the first 2 examples are the same as what FastAI data loader does, but now you'll see from here on you can, well, actually I think even the third one is the same as what the underlying PyTorch data loader does. It just converts a set of numbers, which is a range of 12, into batches of 4, that's 3 batches. Even the FastAI data loader would do that. But what you can define, which we'll look at in much more detail, is hooks that you can add to the callbacks of that FastAI supports. And here is an example. We saw that in the prior cell as well. You provide BSS 4, and after all the iterations are done, you set the T3F, in this case, the attribute to 2. And then you run the, and because you've run the cell, you check that the type is the same as an L, and that the values are what values you would expect to see, and then check that it has, after all the iterations are run, it set the F attribute to 2. The other thing it checks is you can pass in a generator or a iterator into a data loader as input. And in this case, the difference is you can pass in an iterator and then chunk it using the batch size of 4. So here is the iterator that is provided as input, because you say next of IT for whatever in range of 3, that means you're passing it 4 iterables, and you get the batch size of 4 tensor values, even though here it's range and therefore it'll be integers, but data loader converts it to tensors, so you get that. The interesting thing, sticking with this example, is when you have multiple workers going in parallel, then you still would like to make sure that you get things back in order, as long as you're not using a queue which we'll see in the next cell. But right now, if it's a dunder get item, he defines a new class called the sleepy data loader. He calls this is called the sleepy data loader because he's going to make the random function sleep for some time after returning each index. So it goes to sleep for some random amount of time, wakes up, sends you the next value of the letters. That's what this function does. And when you use multiple data loaders, what's the effect when you execute the function? You see two things happening. As you increase, or bottom line, you want to make sure that you still get the same value as letters when you use the data loader and you increase the number of workers that are accessing the values that are passed in. Now, keep in mind that the values that are returned by get item is always in order. So you will get, because that's indexable, so it sleeps, but it returns the next index I. And even if you have multiple workers working on it in parallel, like he increases from 0 to 2 to 4, in each case, what is returned will always be the same as the value of letters, which is the 26.
Srinivas, a question. So why are we calling the list? Because in that third thing, it's return super get item. So we're calling the class that we've inherited from, which is list.
Right. That's because list has the dunder get item. He's using the dunder get item of the list to return the I. This, when you do super, this, if I can select it, that line, when you do super dunder get item, it means that it's the dunder get item of what
the
you're
one that's
inheriting.
defined from the thing that you've inherited from, the class that you've inherited from.
Yes.
And so why are you using the list one though, as opposed to the one that you've got defined in sleepy DL?
No, he is defining a dunder get item in sleepy DL.
Sorry. Yeah. So that's what it's doing. Okay. I see. Yeah.
But
so you don't have to create it. He's being lazy.
Exactly.
But he's just reusing it.
He's just passing it on up to the class he's inheriting.
Yeah.
And how is I defined there? Is that the num workers?
No, I is the index into whatever the letters data set is. So I is the index into the data set.
Yeah, but where does it get defined? When you call data loader, somehow you have to give it that input.
Oh, yeah, that happens. It gets converted to n in the data loader class itself. Because here he's defining sleepy DL, which, where does he pass in T, and he passes in T, if you see, which is a new definition of the, so here T is the data set that is passing into the data loader. And so when you do a dunder get item on T, what you're doing is a dunder get item on the data set, which is what, and the data set in this case, is the sleepy data loader. Sorry, let me start again. The T is a sleepy data loader, which uses the dunder get item of list. Letters is the data set, and the dunder get item gets the item at index I from the data set letters.
Yes, but how does I get defined? How does it know what I is?
I is defined through the data set index in the data loader.
When you say T something, it'll give you that's how you know it's the value of I, because that's.
You mean it tells you that this is the first instance of T? Is that how it works?
Yes, of letters eventually. Yes, of T, which is a sleepy data loader of letters, which means, and the reason it's a sleepy data loader of letters is it will return the next item from letters after sleeping for a random amount of time.
Mm-hmm. Okay. So when you call test when you call the first time call down there, you're calling sleepy data loader for the first time. You're calling T, sorry, for the first time, and then the next time you call it again, and then the third time you call it for the third time. Does that mean that I equals 1 for the first time, I equals 2 for the second time, I equals 3 for the third time?
No, it means that in this case, you will consume all of the letters for I equals. So each of these could have been in different cells because it runs through the entire letters for T. It runs through the entire data set. Here again, remember, he hasn't batched it. So it will go through the entire set of letters because the data set length, or I should say, he goes through the entire, or it goes through the entire data set. And letters, remember, is 26 items total. So the I will go from 0 to 25 for the first, this line of code. It will go through all of it. And then again, for this line of code, it will go through all of it. And then for again, this line of code, it will go through all of it. That's why when you compare data loaders T num workers 0 to letters, letters says all 26. So data loaders T num workers 0 has returned you all of the 26 letters. Right?
Srinivas, would you mind just running that? That I think that will help. So run just, if you just create a new cell and just copy that bit from class sleepydl all the way to the end of where you've defined T equals sleepydl letters, and then if you just print out T, then I think it'll be clear exactly what T holds. So you don't need to have the timing stuff, just so class sleepydl all the way down to just before the time. Yeah, that's it. Yeah, that's exactly that. So in a new cell, I think that would that might make things clearer. Thank you.
But keep in mind that what you don't see here is the fact that you will get each of these after a random period of wait and a random period of sleep. That's what you don't see when you just see the letters. And you can see what happens. The other thing he wants to point out in this is when you have multiple workers, you see the time it takes, the wall time it takes to process it go down from 0 to 2 to 4. Because you have multiple number of workers acting on it. Right. So that's the other thing he wants to illustrate. So I have the comment here, the test check. Well, and the % time tests indicate that as you increase the number of workers, the tests do run quicker. Right. So that's the other thing.
Does number of workers mean anything for us in terms of how many CPUs you need to have, or is it just a?
No, it's the number of. Well, I mean, you can. I don't know whether you can increase. I haven't kept pace, but you can go up to the maximum number of CPUs for threads that your process supports. And I think if you want to use default of -1, then that provides you the maximum number. Yeah.
I think
in this case,
go ahead.
In this case, he's just illustrating what happens when he actually passes in values that are explicit.
So how does this time delay help it to keep track of because I would think that when you do num workers equals something other than 1, then these processes fork into 2 independent processes, and they don't know what each other is doing. So how do they know?
That's in fact the magic of the multiprocessing coordination stuff that he talks about that PyTorch handles. And that's really delicate, meaning that's one of the reasons why he wants to change certain parts, but he wants to leave the underlying MP portions, which we'll touch on later in this lecture a little bit, but he still leaves, as I've said before, right? And if you go way back to the beginning, and he talks about it in the walkthrough, while he passes in a fake loader and I think there's a worker information function and stuff, but at the bottom, he just uses the multiprocessing data loader and the single process data loader from FastAI, from PyTorch directly, right? Because those are, as you said, very delicate things in the sense that if you don't act or if you don't ensure appropriate threading, you can get in a lot of trouble.
So how does the delay, how does the delay that you pass it, the random delay, help it to coordinate among the different multiprocessors?
No, it isn't helping it. It's actually, he's just saying that I can, in a network, if you think of, let's say the letters are coming to you from across a network, then you may get one value A, and then you may have a delay of, I don't know, n number of seconds, and then get the next letter B, and then get a different amount of delay and get next letter C. And he's just illustrating to you that his data loader is capable of handling a delayed network stream of that kind and returning, even in the use of multiple data loaders, the total data set that you seek, which is the set of all letters in order.
Okay, so if you didn't use that delay, then what would happen? I mean,
nothing.
In other words,
you would still get back the same
you'd
thing.
Still get back. Okay.
Yeah, which is what was the example we saw. Although he didn't do it for letters, but that's what RANDL does with a random value. But you could have returned, instead of the random value, you could have returned here. I mean, of course, here he uses stop, but if not, you could use the same, just like you said, we could remove this time dot sleeve, in which case you're just returning these letters in sequence in order with no delay between them. Okay. But here he's trying to illustrate that he doesn't want to get into a very complex example. With a simple example, he's trying to show us that if you have network stream coming at you, a stream of data with varying amounts of delay between the data values that you get, for example, the data values in this case could be A, B, the characters, and you have differential delay between the characters, you can still collect them together and your data loader will still gather them depending on whether you give it a BS of 4 or not give it a BS at all, in which case it will wait till it collects the entire data set. In case you provide it a batch size of 4, it'll, as soon as 4 elements are collected, even though they may arrive at different times, they are collated and provided to you as a batch.
Okay, I get it.
So he's just showing you example of how the data loader works under streaming conditions with varying latency.
Thank you.
Okay, so one question, why he's making this claim that it can handle the stream data? So I thought he is just inheriting data loader from a PyTorch and then he's just using it. So is it he's something doing different in the FastAI data loader than the PyTorch, but still able to manage the all underlying delicacies, or it's a general comment he's making?
No, he has very substantially enhanced the PyTorch data loader. That's, and we'll see more of it as we go through, but I already showed you that we've already seen that he provides you the ability to customize at all of the callbacks that FastAI provides. You can provide different functions. The PyTorch data loader cannot handle streaming data like he does here. The PyTorch data loader cannot change the functions like create the callback, like create item after item. You can't customize at those points with a PyTorch data loader. So he is built on top of the PyTorch data loader. And as I mentioned in the last lecture, the reason he still wants to build on top of it is because of what Joseph just asked, which is the PyTorch data loader has some multiprocessing capabilities that he wants to rely on, and that's very robust and well tested. And that's the reason he uses the underlying infrastructure of the PyTorch data loader. But he customizes and enhances it significantly. For example, the Python data loader cannot support or setting attributes after an iteration is complete, and so on and so forth. So there are variety of enhancements that he has done, and in fact, we've gone through some already, and we'll go through more. So it's incorrect to say that the FastAI data loader is the same as the Python data loader. It's built on top of, but it significantly enhances the Python data loader.
Okay, thanks.
Okay, now also to answer the question of if you now until now what we have seen is just using get item and data loaders which are still iterable in the sense that they are providing you an index. So you have a data set and it's indexed. Now it can come to us at different delayed rates, but it's still coming to us in a sequence or a defined sequence which is indexable. The next cell, what he's trying to show is if you create a queue where every item of the queue can go in any order into data set. So for example, this is an example of only using a dunder iter versus a dunder get item. And he's then using or defining instead a sleepy queue, again with a varying latency. And in this particular case, what we'll get, because it's not an indexable item, it just comes to us as iterable value. And because it's a queue, it can come to us in any order. Therefore, all you can check for after the data loader has built it is that its shuffled value is the same as the original value. You can't ensure order in this case because it comes to us in random order. So here you can see that he defines a queue, and in this instance, there is, because it's a queue, it has an iter and there's no indexing, so no guarantee of the order in which things come to us. So when we compile it using a data loader, all we can ensure is that we have managed to compile all the items, but it will be in shuffled order. The order is not guaranteed because this is not index, it's an iterable.
So Srinivas, shouldn't it mean that it could be shuffled? Or rather, more likely than not, it will be shuffled.
Yes,
but it not necessarily means it has to.
That's more accurate way of saying it. Yes, more. It is highly likely
that
it will be, and more importantly, you cannot guarantee that it will be in order. So you can't check for it to be in order.
Okay.
You could get lucky and it can be in order, but you cannot check for it to be in order.
Okay.
Right. So that's why you check for test shuffle rather than test equal. Right. Okay. So now we're ready to look at the second way of specifying the class, or actually a callback, that I promise we'll get back to. So remember that the first way of defining a function or changing the function CreateItem is to define a new class and inherit from data loader and then change the CreateItem function. As I explained, what we are doing by doing this or defining this class and changing or redefining CreateItem is we are customizing the CreateItem function within the standard FastAI data loader. So we are saying, don't use the CreateItem function that this FastAI data loader already has. Instead, replace it by what I defined here. Now, an even easier way of changing this, and I think Rekil alluded to this, because this doesn't require us to understand inheritance and OO, object-oriented programming and all that. Instead, what you can simply do is define a function, and if you see the code, you can go back and compare the line of code. You're just defining underscore rand item, and the reason for the underscore is it's a private function that you don't want used elsewhere. These two lines are exactly the same as what you have defined in CreateItem. If you see, if you ignore this line, these next two lines are exactly the same as these two lines. And you have just defined the underscore rand item, pass it as, notice that there is no self, because you're not, you'll see that in this case, you're redefining the CreateItem function within the data loader. In this case, you're just defining a function rand item, passing in as, defining it using these two lines. And then when you create a data loader, you say CreateItem equals underscore rand item. That means you are changing the definition of the CreateItem function within data loader to be the new function that you have defined. This is a much simpler way of changing the CreateItem or any other callback that your data loader has. So
Srinivas, a question for you. Why do we need the S argument there? Because you don't use it at all. The S parameter in rand underscore item.
Good question. I think because the CreateItem takes in a parameter, if I'm not mistaken. The CreateItem uses the S index. Hang on, where am I? So here, see, the rand item is S, and here you define self and an S. Here also you do not. So maybe you could even try it without giving it an S and see that, because as you can see here, he has called, well, here he's just calling the instance of this, but he hasn't passed in any S. That's a good observation.
No, you're right, though. I think whatever he's used for the previous one, he's decided to just use
he's just trying to be consistent. But even in the previous one, to your point, it may not be necessary, and you could potentially try it with that. Yeah, so it is. It's
the way the CreateItem is defined in data loader, it takes an S. So you need to have an S there. Because basically when you're trying to create the item, if you remember the CreateItem, I think it calls like do batch and all that stuff. And for each of them, you need to keep.
Yeah, that's what I was doing here. So it's self of S. So that's why he keeps the S there. Right. If S is none, then so it's the index into the data set. So that's the index. That's the I question that Joseph was also asking earlier. So, but now how does this work? That is to say, why is it that you can define a function outside of the class, pass it into the data loader like we have done here, and have the data loader accept it, and instead of using its own CreateItem definition, which it has inside of the class, it uses the function that you have defined outside. So how does that work? And what infrastructure does FastAI have which enables you to do that? And that's an interesting question. And here is how that works. So he uses, if you will, a decorator, and you can see the decorator at func's keyword arguments. So here's what this decorator does. First, look at two lines of code, or a set of lines of code here. He has defined underscore no-op methods to be a list, because he's using a split function on a string, and he passes in all these different callbacks, right? Before iter, blah, 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 after iter, and so on. And then he adds the no-op methods to this list of functions that are actually used in the remainder of the data loader code. So for example, this CreateItem, we saw the line of code in data loader that defines CreateItem. But here's how, or here's the underlying infrastructure that he has built to be able to provide a redefinition of any one of these functions and pass it in to the data loader and have the data loader use the function you're passing in instead of either a no-op or a function that it already has within it. And the way that works is the funcs keyword args decorator, and the code as to how it works we'll see in lecture 9 or 10, but here we are just trying to understand what it does. So the funcs keyword arg decorator, it looks for underscore methods within the class that it decorates. And if there is an underscore method list, then it says that for that class's init, the ** keyword args that are passed in to this particular class's init are defined in the underscore methods list. So what that means is whenever you pass in any one of these items and any one of these callbacks and you equate it to a function, the funcs keyword arg decorator will convert the function you pass in to be the actual function that this keyword argument uses instead of either a no-op or what it already has defined within the class. So that's the magic by which this decorator and what it does, that is, it relies on an underscore methods list, which it grabs and shoves it into the ** keyword argument of this class is under init. That infrastructure is what allows you to redefine any one of these no-op methods or any one of these methods. So basically any callback defined in the underscore methods list can be replaced. So you can see the power of what he has built, because that means essentially, of course, he illustrated the example of changing the CreateItem function, but you can change the create batches code, the retain types code, the get IDs code. You can redefine sample, you can redefine before iter, after item, before. Any one of these functions can be redefined to be what you want it to do and just pass it in and that'll work.
So I might have missed this, Srinivas. What example is there where you'd actually want to not use the class-based one and you want to use this method one? What's the what kind of use case would there be for that?
Oh, he just showed you a use case of, we just saw a use case of utilizing the infrastructure to support streaming data, which you wouldn't otherwise be able to do. We just used the redefinition of CreateItem to support handling very large data sets, for example, or handling a network stream that depends on some token value or a stop value. Of course, he illustrated it using a simple random item or the random.random, and then when it's greater than 0.95 stop, but that it need not be that. It could be, hey, I want to watch this network stream and continue to gather my input until I come up on a sentinel value, in which case I want you to stop. So you can handle a data stream across a network or a streaming data, which the PyTorch, to my understanding, doesn't support, and instead by redefining CreateItem, you can support. And towards the end of the lecture, we'll see that at least 3 of these callbacks are used in the transform data loader to provide us the ability of running a bunch of transforms, which is essentially a pipeline, at particular points of processing our data. So essentially think of everything we are doing, as I mentioned in the very beginning of the lecture walkthroughs, a lot of it is how we handle data, how we customize data. So think of the whole preparation of data as, a sequence of steps. What he has allowed us now to do with providing this kind of an infrastructure in the data loader is have slightly different behavior or customize the behavior at every step of that process along the way. That is, you could define a function after you get a single item, which treats the item differently or does certain things. So for example, and I'm kind of revealing something which we'll get into with more concrete examples, but I'll just talk to it and then we'll look at the concrete example at the end of the lecture is, after you have created an item, you can run a pipeline in order to prepare the item before you batch it, before you collate it into batches. And again, you can run a set of transforms or functions at the time before you are sending it to getting batched. That's the before batch callback. After you have created batch, you can again run a set of functions after you have created the batches. If you're running a bunch of iterations, then you can execute a set of functions before you begin any of your iterations and after you've completed all of your iterations. Now, keep in mind that this before iter and after iter callbacks are before and after the iterations for generating your data, right? So, and of course, they can also be defined depending on your callbacks of where in the process of generating your data you use them. But the point is that each of these callbacks, that means at each of these points when you're building your data, you can run different functions, and we'll see the usage at least for these three callbacks: after item, before batch, and after batch, toward the end of this lecture.
Okay, I have a question. So up above where, can you go back up above? Yeah, so I've never seen this two decorator thing. And so I have two questions. One is, how is this, when you stack decorators on top of a class, does that mean that the class is decorated by both of these? Yes. And then the second question, is, what does that first decorator actually do?
Yeah, I haven't looked specifically, and in fact, one of my intentions is eventually to document all of the decorators one by one and what they do and the code. He does get into each one in the final two lectures of the walkthroughs. The log args, I'm sure, is something that helps us log certain arguments, but to tell you the truth, I haven't pursued specifically what the log args decorator does in this context. But to
Joseph,
answer your first question, Joseph, yes, the decorators work inside out, meaning in this case, they may not be relevant because they may be decorating different parts, if you will, of the class. But you could decorate the same functionality, meaning you could have at A, at B, at C. You could have any number of decorators, and at A means you would decorate A of the class, pass it to the name, and then if you have a B on top, that would mean that function or then decorates what is returned to it by A. And then if you have a C on top of that, that would end up decorating what is passed to it by A and B.
So it's bottom up from the list of decorators, from the stacked list of decorators.
Yeah.
It starts with the bottom one and then the next one.
Think of it as a function, right? So if you've got data loaders here, what's first applied to it is function quarks, and then what's applied to log args is once you've applied function quarks to the class data loader.
Mm-hmm. Okay.
Yeah, but to your question, yeah, I've not pursued what log args does, and one of my goals, as I said, he uses a bunch of decorators, as we saw. In fact, I didn't get into it, but one of the ways by which these keyword arguments, instead of it being just ** quarks, they allow you to find out what they are if you use Shift Tab, and for that he uses the @delegate decorator. So he uses a bunch of these kind of decorators, and we saw that even when he does, I think, properties and @props or something like that. So he uses decorators a lot to keep the code compact. And
I had a question with that. Srinivas, like difference between getAttr, the delegates, and what we just saw now, func squads. Is there a simple way to kind of simplify and say what the difference between these things are?
Sure. See, I think getAttr says if you do not have an attribute for the class, like for example, you don't for a data loader, if you say, if you do not have an attribute for a property or for, then the default value of something that you do not define is what you use in default. So for example, what you define in _default is a data set. So when an attribute is missing, then it assumes that it will be data loader dot dataset dot.
Okay.
Right. So the get attribute inheritance is to address a missing attribute, and that particular get attribute function definition will look for _default. And remember, in case of where was it? In this case, it's a data set, and I forget in which example we looked at. It was string. For a data set, I believe it will string. So it will, then you don't supply it, or it's because it's a missing attribute. And if you just say dataset.show, it will assume it's dataset.string.show. Right. So in this case, if you don't supply dataset, it will assume that it is dataloader.dataset.show.
Right. Okay.
Right. That's what getAttr does.
So getAttr and _default is the pair there, right? They work in sync.
I'm sorry.
So getAttr and _default are the pair which work in sync for.
Correct. They work in sync. Funcs, keyword args, and _ methods work in sync.
Okay. And what does, I mean, to be like, doesn't it kind of do the same thing?
Not.
Or is there, okay, there's no finding the attribute if it's missing part, but you're only setting these attributes. That's the difference.
Yeah, and you're setting it in the passed in keyword args argument.
That is the same part though, right? Like the quarks part of it is, my understanding was like that shift app thing works in both these scenarios.
Oh yes, that works. That's through the @delegates decorator. That's different from the get attribute.
Okay.
That delegator, again, if you can see, can you see my screen that I'm pointing at, the make delegation work in Python?
No, but okay, I see. I know what you're talking of. Okay, so that blog post is what? Okay.
Yeah, I can, let me see whether I can, well, I'll have to switch back and forth.
Yeah, that's
so
okay.
I can talk to that at the very end, but there's another decorator. He doesn't use it here, but that's the decorator that used to illustrate the keyword args. And I'll post the link to that and you can kind of go over that, but that's a different @delegates decorator.
Okay. Okay.
So that's why I said, at some point, and in fact, I think somebody had already done a version in FastAI forums of the decorators and what they do, but I think he has subsequently enhanced or modified as Jenny is apt to do. So I wanted to kind of do it by the end of this walkthroughs, define all of the decorators and what they do in one location. Okay.
I have one more question. So I get after item, before batch, and after batch, like where you would use them. Is there an example that he points out where you would use like before return and after return? I'm kind of finding it hard to place where in this pipeline of operations would you use them? Could you use them? Why would you use them, sort of a thing?
Yeah, no, I haven't seen examples yet. At least I would have to go to my notebook to see whether he uses in any of the other notebooks from 4. Well, he doesn't use it in 4 either, but 5 through 10 I haven't seen. So that's a good question.
Okay.
But typically he is, quite smart about doing these things. So I'm sure the reason he added them was because he has used it or has felt the need to use it somewhere.
Okay. And I mean, it took me a while to figure out the before batch. So if everyone else just needs kind of context, like after item is kind of used like at the data set point, right? And once you get your data sets in and you're trying to make it into like resize would be a transform. Is that the after item one?
Yes, that's correct.
Okay.
So you get an item, and actually when we go to transform data loader, we'll see an example of the pipelines in each. But yes, but to your question, let's talk about it right now. I think after item will be after you have received a single item from your processing actions, right?
Okay.
So exactly to your point, if you get a single image, let's say again, the same standard example of whatever the pets data set, which has an image and a label. So if you get an image, then so that image is a single item and you want to resize it, that's when you would do it.
Do that, okay.
Correct. Now, before batch, to be honest, even I still have difficulty of kind of grasping.
So before batch, I kind of figured out is more of an NLP thing. So let us say you're making a batch of different sentences. Now, each of these sentences will have different lengths. So your after item transform is already over, right? Because each of the sentences came in, you numericalized them, you did all the coding into whatever those numbers are, the vocabulary is being used. Now you have like you created a batch, let's say of 10 sentences, but now each of these 10 sentences have different lengths. So that's why he uses before batch for padding.
Got it. So see, that's, in fact, it's interesting because I had not grasped where it would be used, but that's an example of where he introduces callbacks, which may not be immediately apparent in the example we are staring at, but there are good examples.
Right, yeah. I did the command F and tried to look for before batch I found, but I couldn't for some reason find before it or an after it. Or
yeah, you'll have to wait to see where he pulls that off.
Thanks.
That's good because I was struggling with, okay, where have we used before batch and why would we use it? But that's a good example that you just shared.
Yep. Okay,
so that essentially shows, I think, and we'll get, as I mentioned, toward the end of, hopefully within the next 20 minutes or so, we'll get into the transform data loader, which is a different notebook, and we'll revisit it. Kibi has already shared the code, but given the data loader, then we get a more nuanced understanding of how is the transform data loader, the TFMD DL, different from a data loader. But before that, let's just wrap up the remaining pieces that we haven't touched on or haven't explained. Again, the explanation, as I've said, is more like a shuffle level, because if you get into the multiprocessing code, I can't explain all the details of that, but now we are back into actually the data loader code itself. And the rest of the
Sorry, Srinivas. Just one question before we move on. I just want to make sure I understood this. So, we looked at one function that had an underscore before it. Next, what was that called?
Yeah, the rand DL or something like that, which, he does that primarily to say it's a private function, right?
Rand items, right? Okay. So if I just want to confirm I've understood this correctly. Are we saying that rand items, so underscore rand items, is a function that can be used outside of the class, while as there exists a rand items that is used within the data loader class? And we're using, and so he's just showing how you can use this rand items outside of that class?
Okay, so there are two pieces of what you said, and I'll separate them and explain each of them. So this underscore rand item is just a function. Think of it as any good old function that you define. What you're actually doing is redefining CreateItem, which is an function or a method within your data loader class, and saying that the new data loader that I'm creating, I want you to replace the CreateItem method, which has a definition within the standard FastAI data loader class, and replace it with my function. That's why the underscore, my private function underscore rand item. Okay, so what it's saying is, I want you to replace CreateItem function, which is actually a method because a function within a class is a method. So the CreateItem method within the data loader, I want you to replace it with my definition of what it does, not use the standard definition that you already have within the data loader. Now, as I explained, you can do that. In this particular example, he has just used CreateItem as an example of a method that can be replaced with your own function. But as I just went through, you can replace, and if you saw in the data loader code, this is the function that is getting, or the method that is getting replaced. What I explained is any of the methods that is in the underscore methods class, which includes all of these methods, which currently, and by currently I mean in the default implementation of the data loader, these methods are no ops. That is, they don't do anything. But there are also methods such as the CreateItem method and all these methods which have been defined in the data loader class. And any method in the underscore methods list, which is a combination of the no-op methods and all of these methods that I've highlighted, can be replaced by any function that you provide.
Okay, understood. Yes, thank you.
Okay. So now back to what we were talking about. I think just wrapping up the details of the data loader code and kind of complex why he has to rely on the PyTorch data loader. I already touched on this, that the PyTorch data loader expects.
I have a question about. I have a question about what you just went over, where just a few lines above, right at the top, I need a little more room there. Yeah, so he defines no-op methods, then he has this loop for O in no-op methods, then he defines methods, underscore methods. Why doesn't he define why doesn't he concatenate the no-op methods? In other words, why doesn't he put that command underscore methods above the loop and then have the loop over methods itself instead of no-op methods?
I think the no-op methods for some, this particular function, it's an exec function. That means you run this, if I recall, and maybe people more, because it just uses this string and it says definition of O is self, X, none, star args, return X is basically is running these no-op methods.
Yep.
So he's just making, because no-op method, he hasn't defined them to be no-op in this, right? He just said no-op methods is this list. What he does, I believe, by running these two lines of code, he ensures that every one of these no-op methods is actually a no-op. And then he combines it. So that's why he does the code here of these two lines of code. He does it in order to execute the no-op methods and make them basically, returns none for every one of those. And exec basically just says, if you go back to Python exec, it essentially executes this string.
Right. So if there's an error, if one of those methods isn't a no-op method, then it throws an error when it runs the exec.
Well, it isn't none. It makes all these methods none, return none. By running
makes
this.
Them return. Oh, I see, because it sets X equals none. I see.
Exactly. And then he returns X, which means he ensures that they are no-op methods.
Well, I think each one of those methods return the X that is passed. So that is an operation because each one of those methods just returns what you pass. When Python encounters a class that has each time that the interpreter goes on a class, it executes each line. So when it encounters the first no comment, no method, it's assigning that. So it will execute it in that moment, that for the no methods, and it will. I don't think it is like a lazy. It's like a fun way to find methods that just return what you pass. So take that as if the class has that 1, 2, 3, 4, 5, 6 methods wrote as return x with the same, how do you say, with the same signature. And after that, it reads the not methods, just the name, not the methods, because when you exec, those methods are already of yourself or of your class, like if you wrote them inside. So after that, the methods are concatenated, just the names with the author's names, and then it splits those names, but not the methods in itself. So I just wonder what will happen if instead of write one of these methods, you just try to override any other method, passing it as well, just to change them. That's it.
Yeah, I think the func keyword directly separates only this list, which is in methods. If you try to change it, any others may or may not work. I haven't tried it.
Okay.
So what, to wrap up the rest of the code in the data loader that interacts with the PyTorch code, here's where this is the line he keeps referring to, which is hokey. And as I said, even I don't fully understand why it has to be in this format or be as it is defined here. But what he is doing, as I've said before, is uses the underscore loaders as is from PyTorch. And I'm glad Jeremy figured it out rather than any of us having to figure it out. But
I figured it out that the other day because I was working with something like this. That self-fake L num workers equal 0. I don't know who initialized the num workers, but at least on my example, it got 4. So it is false. And if you scroll off, that loaders is...
yeah, I'm getting into that right now.
That loaders is... okay.
Yeah, so that's what I'm explaining. That's the rest of my explanation. So here, as you see, he uses self.fake L, which is defined here as the class underscore fake loader. And as he explains in the walkthrough, which I have included in the comments code that I have, the PyTorch data loader expects to get an object of type fake loader with particular values for pin memory, number of workers, and timeout, and blah, 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 as well as the values that he defines on the line of code above that. That's the expectation PyTorch has for it to work correctly with all of the multiprocessing data loading stuff. That's the reason that he defines or uses that definition of self.fake underscore L, which he defines as the fake loader. And he defines the fake loader itself for FastAI here in the class. And as I've said, PyTorch expects an object of this type with a particular set of values. So unfortunately, as he explains in the walkthrough video, this means that FastAI data loaders have been now tied to the internals of the PyTorch data loader, which obviously is not a good thing to do because you're now susceptible to changes that PyTorch might do in future revisions and your code is broken. So he says, hey, we'll keep a tight lid on it and keep watching it, and also encourage them not to screw with it or make the API better and not have us do this kind of tied to the internals issue. But for now, it is the way it is, and he specifies the set of values that he gives here in this list to hold the set of values here, and then defines the init. And this is where, for example, he sets the values of dataset default worker init function, which is something that PyTorch infrastructure itself introduced in the 1.2 version. And that callback within the PyTorch data loader infrastructure is what is called every time a new process, that is a new thread or worker is fired off. And in order to use that, there's a worker information function that PyTorch uses. So he uses his good old store attribute to store the attributes on the fake loader of the data set, the pin memory, the number of workers, and the value of timeout. But he gets that from the _whiff, which is the self.workerinit function, which again, he defines his own _whiff, where he sets the number of threads to be 1. He gets the information from the getWorkerInfo function that is available, sets the data set, sets some values of the number of workers, the data set offset, that's the index of the data set. And to Joseph's question, this is delicate parallelizing things automatically that needs to happen in a precise way, and each worker then gets a separate random seed to prevent the horrible things that could happen if the seeds by any chance get duplicated. So he sets the seeds he gets from here, make sure all these are set up properly, and then in the iter of the fake data loader returns back to our data loader of the sample and then create batches. And that's when we fall right back into our own data loader. But that code is fairly complex, and I'm just glad it works. And I've just jotted down the explanation of what it's supposed to be doing, but obviously I haven't gone into and run each line of code if it works. I believe it does what he tries to explain. It does. The one other thing that he touches on is, after all this complexity, there's one last bit of complexity still left, which he customizes again in FastAI. And that is the fact that just before a batch is created, after going through all the CreateItem, create batches, and eventually come to create batch, and PyTorch again does two things or calls different functions depending on whether, as we saw before, the data set is an iterable data set or it's a indexable data set. And we saw the difference between the two, and depending on that, it applies a collate method or a convert method to the batch. And each of these are PyTorch functions, but again, he customizes them in FastAI. And the reason for the customization is the fact that these convert and collate handle a few more data types. And I think from what Rekil pointed out in the other example, I think in this instance also he supports these types because he wants to handle language, vision, as well as tabular data and so on. So he enhances the collate and the convert functions of PyTorch, converts them to FastAI collate and FastAI convert. And essentially what they are, they handle a few more data types beyond what the native collate and convert of PyTorch handle. So that's what he says here. PyTorch by default calls default collate, sorry, not just collate, but default collate and default convert. And they take all the items in your data set, turns them into a batch. If you have a batch size, or use default convert if it doesn't have a batch size. And FastAI collate handles a few more data types that PyTorch collate doesn't. For example, you can see the is instance B sequence, so it probably handles a sequence, whereas the default collate of PyTorch probably does not handle a sequence. Right, and this enhancement that he makes is one of the reasons he says that Let's see, let me see whether I can show you that. Is the reason I've stopped sharing for a minute. And let me see whether I can, yeah, show you a different screen. So can you see this screen where it says make delegation work in Python?
Yep.
Okay. I'll get to that in a minute because that was the other decorator I wanted to show you. But let's look at this. This is the text data notebook that Rekil was mentioning earlier. This is the equivalent of the video data or the, the default data loader is what we were going through, which is in O2 data load. And this is the language data loader that is in 31 text data. But my point is, he talks about this in the walkthrough. The entire language data loader is in one screen that I have up here. My point isn't to go through this because it's fairly complex, but the point he makes is the reason that a language model data loader, which is usually very complex in any other library, and he can make it all or show it in a single screen of code, is because of all of the infrastructure, including handling different data types and the FA collate and the FA convert functions customization that he does. So we'll, see, he unfortunately doesn't have a walkthrough which covers the language data loader, which I wish he did. But the bottom line is that he's able to create a dense single screen piece of code to handle a language model data loader as compared to several screens of code or very complex code. And that is because of all the customization that he has done in the default data loader. Before we move off this set of windows or tabs, this is the @delegate decorator description and functionality. This is the other decorator that Rekil was talking about, which essentially allows you to view what is passed on into a class as ** keyword args. So I think somebody else touched on this in a very early class, but I would recommend you go through it. It's a good example of what decorators do and how Jeremy continues to enhance anything that he does, because earlier versions of FastAI, and I myself suffered through it, is it just says ** keyword args and you don't know what keyword args are being passed in. And instead, this particular write-up that he has covers the delegate decorator, as well as I think the code for get attribute as well. But we'll get into that in lectures 9 and 10. I just wanted to show you where it's at. Okay, back to sharing the other notebook. Hopefully we'll be done by 9:45 at the latest, because we're almost done with this code. Can you see the O2 data load code?
Yes, thank you.
Okay, so I think with that, we are pretty much done with the basic data loader. It's fairly complex, as you saw, and certain pieces are just explanatory, but it also shows you all of the places where customization can be done, which in turn takes us back to the O3 data core, which O3 data core notebook, which has the transformed data loader. So now that we have seen a data loader, we'll get or be able to appreciate or understand better what a transformed data loader is and what it does. So what a transformed data loader does, and here I'll call your attention to the _batch transforms, which I'm the cell that I'm just executing. And if you see the transform data loader class, and interestingly, the very first decorator is the @delegates decorator that I just pointed you to. But more importantly, the transform data loader inherits from our data loader class that we just spent the last 2 hours in the last lecture before that going through. And what it does, as you can see, when you look at its code, is the specific list of callbacks that are specified, in batch transform. So these are in underscore batch transform. There are 3 specific callbacks: after item, before batch, after batch. So what it does is for every name, NM is usually the shortened form of name that Jeremy is habituated to using. For every transform in batch transforms, it converts the keyword args of that to be a pipeline. So what it's doing in essence is after you grab an item from the data loader, or from, after you grab a single item in the data set, then you have a pipeline, which is a set of transforms that you then have in your after item callback. Same thing for the before batch callback. You have a set of transforms that are made into a pipeline. And same thing for after batch. You have a set of transforms that you convert into a pipeline. So in effect, what it means is the specific list of callbacks in the underscore batch transforms list, they are turned into transform pipelines. So after you grab a single item in the data set, you run a pipeline, which is a bunch of transforms on it. And after you get all the items, but before you collate them, and this was the part that I hadn't thought of where exactly it's used, but Rekil solved that problem for us and gave us the insight that, this is used, for example, the before batch, which is what the callback is at this point, is used in the language model data loader. And so after you get all the items, but before you make them into a batch, you run a set of transforms. And then there's after batch, which is also a callback, and you run that transform pipeline. So you run transforms, which are collected together as a pipeline, after an item is returned to you in order to prepare the item. And an example that Rekil already shared is you want to resize an image before you batch the images. You do that after every image is given back to you as an item. And then in image processing, typically you wouldn't use the before batch, which is the reason I didn't immediately think of an example, but you therefore go to after batch, and after you've batched it, you want to run a bunch of transforms. That's what the after batch callback does.
Can I ask a quick question? Sorry.
Yes.
Are we reading too much, or why is after item sitting in underscore batch transforms?
Yeah, it's just
I know those are the 3 I think we most commonly use in the data loaders scenario.
Correct. But it's just the, what I would say, just the, he could have called it anything. It's just a name that gets passed in here, right? Because, and that's, now it's buried in the code, so it's probably what it will remain as, but you're right. He could have called this, convert to pipeline transforms.
Right, something like that. Okay, yeah, just check.
Yeah, so you're right. It doesn't have to be called batch transform because it applies to after item as well.
Right, okay.
Yeah, that's right. But it's just the list that it's passed in, but unfortunately it is tied into the code.
Yeah, sounds good. Okay.
And what is interesting, and we have touched on this, and we will touch on it in the next lecture as well, is when a pipeline is constructed, if you need setup within each of the transforms, the do setup runs the setup for each transform within each of the pipelines that are provided in, or I should say, it runs setup for each transform within the callbacks. Okay. within the callback specified in _bat transforms. And that's where so how is transform data loader different from just the base data loader? So the base data loader just returns you the item or the batch or the set of batches. In this case, the transform data loader has the ability to convert or has the ability to make the transforms that you supply to each of the callbacks, after item, before batch, and after batch. They are converted into pipelines. Any setup is run, and then you can do what you want to do with that data. Right, and that's the difference between a transform data loader. So a transform data loader is a data loader that has 3 callbacks, and the 3 callbacks are each transform pipelines, right? So this, now, why is that important? That's important because each of these transform pipelines can run setup, can run encode, can run decode on the data that you provided, right? So as you're preparing the data to be processed by your algorithm, you will be encoding the data. But what is interesting and most important, and we'll get into that a lot more in the lecture 4 as we dive into very specific examples of transform and pipeline. But the important point about transforms and pipelines is the fact that they remember where the data came from, quote unquote. That is, they remember that the data that is provided to you is an image. Therefore, when you decode, you're able to show the image. And that happens because the show method calls the decode method, and which puts the types of the data that was used to create the tensors, and that in turn enables you to display the image rather than just say, this is just a bunch of tensors. How do I know what to do with it? So for example, you can see that the retain DL is a function to figure out the types during the decode. And so what happens is when you come to do, so let's see, show batch. Yeah, okay, so a show batch. So remember when you do a show batch, which is essentially trying to show what your data is, but by this time in the preparation of the data, all you have are a bunch of tensors. So you could, if you had used just the PyTorch data loader and so on, you cannot execute a show batch because it does no concept of what those tensors are. They're just a bunch of tensors. However, with fast AI, when you do show batch, it in turn it calls, again, this is because of the complexity of all the details that he has to handle, but it calls pre-show batch. Pre-show batch runs decode, and the self.decode batch is what is returned. And ignore this because this is just a matter of, whether you handle tuples and how you handle lists and stuff like that. But bottom line, you have to run self.decode. And if you go to self.decode, you first run the retain DL, which means you retain the types of B. And if the types aren't given, then if you go to retain DL code, this is the function that figures out the types of the data that is needed in show batch. So show batch, as we saw, called decode. Decodes in turn calls retain DL, which runs one pass of the data to figure out the types that are in the data that are attached to the data, quote unquote. And that is what enables us to display the type as whatever we want it to be, meaning which is attached to it as we go through the encoding process. So that piece of infrastructure that we have now seen is what enables a show method or a show batch method to call decode, which in turn calls retain types, which ensures that, and the retain types works because of the type dispatch, and we'll get into the details of type dispatch in upcoming lectures, but it essentially attaches types to the data as we go through the encoding process, so that when we unwrap it using decode, we remember or we can recall that the type of data we supplied from which we have extracted the tensors is an image, and that's why it's able to show the image. So it runs one pass, figures out what the types are, and uses that to display the image. And it also similarly uses it in tabular or in language models when we decode, to either show sentences or to show tabular data. And of course, this is all abstract, and we'll get into the exact, how does function dispatch work? How do the types get attached? And some of that we'll look at in the very next lecture. Questions?
No, but thank you. Excellent work, Srinivas. Appreciate your time and effort.
Sure thing. Welcome. One more thing. I'll post in, right after we are done, I'll post a notebook which I created for the fourth walkthrough, because one of the things that Jeremy does in the fourth walkthrough, it's a good one. I'd encourage people to watch it if you want to understand how transforms and pipelines work. They have seen versions of it, but he kind of brings it all together at a particular level of detail in that lecture. But he does one of these annoying things where he goes back and changes the code and reruns it. So it's, you know, the worst of Jupyter Notebook, in the sense that you can do it, but then it's very confusing of which version of the function he's using. So I've kind of unrolled his entire thing completely. So each loop that he takes, I have unrolled in the notebook, and I'll post that notebook. And if anybody wants to volunteer to use that notebook and go through the lecture, that's great. If nobody does, I'm happy to go through it. So we'll wait till Wednesday or so to see whether anybody else wants to use that notebook to go through and explain the fourth walkthrough. If not, I'll do it next week.
That's great, Srinivas. So I have one last question before you go. There's, in this screen that you're showing here, there is a function called PV. It's way up at the top. I'm not sure what PV, I'm not sure what that function PV does, or a method or something.
Do set up for name in this PV app string. Yeah, it almost seems like it will be like an exec. Oh, print the value f string, setting up the name keyword guards and with the verbose option, I think. So that would probably print it to screen. I haven't checked. Let's see. But my guess, just staring at it, is
it's just a message that says that what it's
setting
doing.
Up. It'll just print setting up this keyword guard this, and with the verbose option.
Okay, so all it's doing is printing a message on the screen.
Yeah, that would be my guess. But you know, we can do a double underscore PV to see whether it gives us question mark PV. See whether it does. Well, PV text verbose, just like I guessed. Yep. That's what.
Oh, if it's verbose, if you've got it set to verbose, then it prints that thing. Okay.
Yeah.
Okay. Got it. Thank you.
Okay, that was a lot, but it's one of the deeper parts of FastAI. The data loader is a fairly key piece, and as we saw, he has provided a lot of flexibility, but also a lot of complexity that comes with it.
That's great. Thank you, Srinivas. I'd like to echo John's comment and thanking you for this, because you're doing a terrific job at this, as only you can. I mean, I don't see anybody, I can't do this. You're doing a great job of showing us the innards of the library. I appreciate it.
Thanks. Okay. Off in 15 minutes to hands-on machine learning. Thank you, everyone. Thanks, and I'll post the notebook for the